Am I audible in the back? पीछे सुनाई दे रहा है? Is it better now? Okay. So, what were we doing in the last class? Figures of merit. Okay. So, what are figures of merit? What are figures of merit? Okay. So, there are some performance or some metrics through which you will be able to compare two different designs or two different products. We took the example of diamonds. We said for diamonds, the figures of merit could be obviously the weight, and then color, cut, clarity, so many things. And similarly, we said that if we say that, in SRAMs, area is diamond, then something like that would also appear for memories. And then for memory cells, which are repeated millions of times on a chip, there are bound to be many more figures of merit than just the area. And we looked at a wide range of them. Some of them were functional, some of them were performance based, and some of them were power. And a few of them were actually both power and performance and things like that. So, which ones were functional figures of merit? Or which is the most important figure of merit? Let's look at it again. It is the area. Undisputedly, the most important figure of merit for a memory cell is its area. Okay. Then, after area, uh, which are the functional figures of merit that we looked at? Cell stability, we said it is like the safety of a locker in a bank. Just like the contents of a bank locker should remain safe, whoever comes, goes, enters, does not enter, someone has one key, but not both the keys, nothing should impact the contents of my locker. So the contents of the memory cell should remain safe. In those terms, the stability of the cell is a very important functional figure of merit. Is there any other functional figure of merit? Write margin. Because when you want to write, again, it should be functionally possible. So write margin and static noise margin or cell stability are functional figures of merit. इनके बिना आप जितना अच्छा एरिया दे दो, however good an area you give, doesn't make any sense. So if you want to purchase a locker or rent a locker from a bank, they say, oh, we will give you this locker for free. But then you don't know if the stuff will remain safe. Will you take that locker? So whatever be the area, whatever be the cost you are paying, if the functional figures of merit are not met, it's useless. Are you with me? Then we looked at performance figures of merit. Which are the performance figures of merit? Cell current, bit line leakage, write time. So in this, the bit line leakage was one where there was a bit of a confusion. Where the first vote was, oh, bit line leakage is power figure of merit. Okay, it is a power figure of merit. But is that the primary impact of bit line leakage? No. What is the primary impact of bit line leakage? Why? Why is performance the primary impact of bit line leakage? Because you can trigger the sense amplifier only when the sufficient differential has appeared at the bit lines. Now, bit line leakage delays creation of that differential. Because now it is not just about the discharge rate, it is also about the rate at which the other bit line is also leaking. The more the leakage, the slower the differential creation. The discharge rate may still be high, but the differential creation slows down. So it is a performance figure of merit. Now, because it slows down, my reset also needs to come much later now. So what happens? For a much longer duration, the word line remains to be on. Word line remains on for a longer duration means bit lines will discharge for a longer duration. What does that mean? More charge will get dissipated, which I have to replenish during the next pre-charge phase. So more power. So first, performance, and then consequently also power. See, what is one very important thing that you need to understand is that in most cases, performance and power are very closely linked. You want to improve performance, you have to improve power also. In most cases, unless you're talking about leakage, dynamic power and performance are very closely linked. Are you with me on this? Any questions until here? Now, which were the power figures of merit? Retention voltage, overall leakage. These were the power figures of merit. Why is retention voltage important? Power figure of merit. See, for a large amount of time, memory is not active. And in advanced SOCs, where there is so much integration happened, there are so many functions on one die. Not every function is used at all the time. See, when you are just texting, are you using the GPU engine? No. But there is so much memory in the GPU engine. Not just the engine is off, the memories are also kept in a low power mode. They enter into a low power mode by pushing them into what we call as retention. Retention means contents will be preserved, but leakage has to be reduced. How do we do that? We do that by lowering the supply level. Why? Because leakage is exponentially dependent on supply level. So if we reduce supply level, we will exponentially reduce leakage. Now, the lower that you can go, more leakage friendly you are. Therefore, retention voltage is a very important figure of merit there. Are you with me? And then leakage, that is obvious. You want to reduce leakage so that the standby time of your device can be increased. So figures of merit was the first thing that we looked at. What was the next thing? How to size. So we looked at, okay, area is always paramount. We also looked at that, okay, for stability, I want pull down to be larger than the pass gate. For writability, I want pass gate to be stronger than the pull up. So we somehow arrived at a conclusion that pull down has to be the strongest device, then pass gate, and then pull up has to be the weakest device. In fact, we did also say that pull up is probably the weakest device in the technology also. In the entire chip, the pull up of the SRAM cell could be the weakest device. Why? Because you want to save area. So you want to keep all the devices as small as possible. Now, when you keep these devices small, you want to keep pull down also small, you want to keep pass gate also small, all of them you want to keep as small as it is possible for you. And when you do that, what happens? Pass gate, despite being the smallest, might still be strong enough. So what you do, you also increase its length. Or in many cases, we will just look at the memory cell layout, you will see that you can even do DRC violations. You can go beyond the minimum length, minimum width that is prescribed by the technology. Because as you do that, you at once reduce area further. You anyway want it to be weak, so you reduce area further. to gain on both the axes, writability and area. Are you with me? So while there are just 6 transistors in a memory cell, it is fairly complex to design. Are you able to see this? We have already seen that uh, stability and writability are completely opposing challenges. If you want make the cell very, very stable, it is no longer writable. If you make it very easily writable, it is no longer stable. So there are lots of optimizations, balancing acts that we have to do when we are designing the SRAM cell. So now let's look at stability once more. This is a couple of inverters, a pair of inverters, and these are their transfer characteristics. Huh? So what I now do is I close this switch. I close this switch. So what happens? Now out 2 and N1 are equal. Am I right? So these two graphs can now be brought together and they will overlap. And they will form what is famously called as a butterfly curve. Does it look like a butterfly? कहाँ sir? कुछ नहीं लग रहा. Okay. Not really a butterfly. People imagine things. So they imagine that these are like the two lobes are like two wings of a butterfly. Okay. Now, over here, we have shown these two lobes to be almost equal. Will they always be equal? When will they not be equal? There is a noise on any point. So when there is noise on some point. Okay. When else? When two inverters are? Same characteristics. When the two inverters don't have similar characteristics, then they will not be equal. Okay. When does that happen? Okay. VT variations skewed. Both have a same beta ratio. They have both skew. They will have similar things. Skew is not the issue. When the size of either the PMOS or NMOS is greater. When the size of either PMOS or NMOS is greater, bhai, skew wali baat hogi jo Madhav ne abhi kaha. That remains the same. Skew will not make a difference. It will just change the shape of your lobes. What else? You remember we talked about advanced applications, modern applications where there can be more zeros in a memory array? We talked about that. Now, suppose you know that there are going to be more zeros in the memory array. And then to reduce the leakage, you design the cell in such a way that zero, there is lesser leakage. Or writing a zero is easier, storing a zero is easier. Let us say. Now, how do you do that? You will make one of the inverters bigger, the other ones smaller. Now, you're not skewing them. Skew, unka P by N ratio same ho sakta hai. Just the size could be different. Is it not? So then you have introduced asymmetry consciously. So जो आपने अब बातें करी, noise आएगा, VT variations होगा, all those will lead to that. But those we are still not talking about. We're not talked about variations just yet. We'll talk about variations, but not just yet. I'm saying by design, you can design these two lobes to be unequal. Okay. And then there is this one definition of static noise margin. What is that? Linked to the butterfly curves. How many of you watched the videos? So all of you would know. What is that one definition of static noise margin dependent on the butterfly curves? When we make a square in the smaller lobe, so the side width of that square is lower. So the largest square that you can fit into the smaller lobe. अभी equal है, तो आपको definition smaller वाली समझ में नहीं आई होगी तब. But we may design an asymmetric cell, and then the SNM of that cell for the undesired lobe is what we are talking about. Are you with me? So what is happening here? Let us say that this was this pair of inverters, and I wrote 0 on one side and 1 on the other. That's like a latch. And on that, I introduced noise also. जहाँ पे 0 था, वहाँ पे I gave a bump. And where there was a 1, I pulled that node down a little. Okay? Now, this is a latch. What does a latch mean? That what you feed into the first inverter, it goes to the second inverter, then it goes back to the first inverter, goes back into the second inverter. So there's a loop, an infinite loop. If I really want to analyze this infinite loop, can I also just open this loop and say that, okay, there is an infinite chain of inverters? Each inverter feeding to the other, जो भी noise मैंने पहले में inject करी, that is fed into the next one, adds up to the noise of the next one. Can I do that? So that's what we do, just for the analysis sake. Okay, this is just for analysis and developing an understanding. So what is happening? We said that, okay, this latch, which is a loop, is actually an infinite loop and therefore an infinite chain of inverters. If I now analyze this infinite chain of inverters, if at the first inverter I had a 0, and at the end I also still have a 0, then it is a safe situation. However, if in the beginning I had a 0, but when noise was injected everywhere, at the end it became a 1. It means in this loop, after some time, 0 will flip into 1. Are you with me on this? Is this clear? So those of you who have watched the video, it might be clear to you. Those of you who have not watched the video, is this clear to you? Everyone, is this clear? What I'm doing is, I've just opened this loop into an infinite chain of inverters. And just like in this latch, I had put an up noise and a low noise, I put that kind of a noise here. Are you with me? And then we see how the device moves on this butterfly curve. All the inverters are same. So the butterfly curve will also be the same. It's not going to change because it's finally the same latch that I had opened up now. So it's going to remain the same. But what I've done is I've put in 2, in 4, in 6 on one axis because they're representing the same node, and the other one on the other axis. One I in 1 and 3 in 5 on the other axis because they represent the same node. And now we give some noise. When we give some noise, we'll follow the transfer characteristics. So I gave noise on N1 and N2 moved like this. Ab N2 pe noise diya, so N1 moved like this. N1, N2 ka noise deke I see that, okay, this is the loop in which my cell will operate. This is the max voltage that will appear at N1, and that is the min voltage that will appear at N2 and the series. Are you able to see this? So my cell remains stable. 0 remains 0, 1 remains 1. Now let's increase the noise a little. I gave some noise. The system moved to, so N2 is a little lower than VDD. Now I add noise on N2 over here. Now my N1 is a little above ground. I add noise again because loop hai, just starting noise. N2 goes a little lower. I add noise again. N1 goes a little further up. Noise again. And you see, N2 almost goes to 0. Noise again. And N1 goes to, N2 goes to 0 and N1 is 1. So what has happened? I entered with a 0 on N1. I ended up with a 1. The cell has flipped. So it is clear that this amount of noise, this particular cell cannot bear. Are you with me? I've moved from lobe 0 to lobe 1. Not acceptable. This noise is too much. So how much noise is okay? Let's reduce this noise a little. And you will realize that the noise that I will finally be able to handle is such that that is the maximum square that I can put in that particular lobe. And SNM being a min quantity, the minimum noise that can corrupt, I look at the smaller lobe. Whichever lobe, the smaller lobe, the biggest square that I can fit into it, the side of that square is my static noise margin. Now, whether I call it the side of that square or I call it the diagonal of that square, will it make a difference? I'm comparing two different cells. I'm comparing sides. एक का side A है, दूसरे का side B है. Versus, I compare their diagonals, A root 2 and B root 2. Can it ever happen that the cell B will have a different comparison? Like, agar cell A was better than cell B, just because I'm measuring the diagonals, can it happen that cell B will now become better than A? No. So you might find some people challenging you and telling you that no, 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 it is not the side of the square, it is the diagonal of the square. You say, okay, na, what difference does it make? I'm talking about A, you're talking about A root 2. Finally, it is the square only. If A is small, A root 2 is also going to be smaller than B or B root 2. Are you with me on this? So whether it is the side or the diagonal, doesn't matter. What is important is that both the cells, you measure either the diagonal or the side. ऐसा नहीं कि एक का side दूसरे का diagonal. You stay consistent. Then whether you choose the side or whether you choose the diagonal, does it make any difference? So that is how we arrived at this thing that the side or the largest square that you can fit into the smallest lobe of the butterfly curve is the static noise margin of the memory cell. Is this clear? Everyone? Any questions? Okay, perfect. So now I have a homework for you. We discussed in the last class that the node Vx over here that the node Vx over here is essentially the inner node of a potential divider where you have RPG, RPD, this is Vx, this is VBL, and ground. Are you with me? This was what we discussed. And we said Vx has to be as low as possible. Why do we want Vx to be as low as possible? जो भी अभी हमने नॉइज कर्व देखा उसके अंदर हमने कहा टोटल शिफ्ट फ्रॉम जीरो is what is the maximum noise margin I have, maximum noise I can induce. Now, when the word line is turned on, there will some current be flowing here. And for any current to flow, this node will have to rise. Whatever is the rise of Vx, that much you've eaten away from the side or the diagonal of the square there. Are you with me? So I usually prefer the term side because you're actually eating away Vx from the side of it. Okay, diagonal karte, now I can't tell Vx is from the diagonal. Vx is taken away from the side of the square. Are you with me? So we want to reduce this Vx. The most or the conventional way of that in which we did it is until, let us say, 65 nanometers was by chain, designing a size ratio, PG by PD or PD by PG. We call this cell ratio. लेक्चर्स में भी आपने सुन लिया होगा, आप वेस्टे उठाओगे, रैबी उठाओगे, कोई भी किताब उठाओगे, उसमें दे टॉक अबाउट दिस thing called cell ratio, which is width of pull down upon width of pass gate. Assuming their lengths are equal, that ratio is the relative strength of pull down over the pass gate. That was old times. But all of you are young. Anyone who is not young over here? Okay, I am young. So now, since you are young, you have to be in tune with the times of the day. So what I want you to do is, you can look at the way Vx is estimated or beta ratio is arrived at in Veste. ठीक है, रैवी में भी दिया हुआ है, दोनों में है शायद. You can look at that. What they've essentially done is they've applied the Kirchhoff's law. They've applied the Kirchhoff's law, saying that whatever current comes here has to be sunk here. How much current will come here? There is a voltage VBL, there is a voltage Vx. So the VDS of this transistor is VBL minus Vx. There is VWL and there is Vx. So the VGS is so you can find the current in this transistor in terms of Vx. We can consider that as Vx. We want Vx to be very low, all of us. So let us assume that Vx is actually low. If Vx is low, then this device is going to be in saturation. If Vx is low, then the pull down is going to be in linear region. Just the equation has to be different, but the current has still to be the same. Now, use different values of VBL, VWL. कल ऑफिस आवर्स में someone came and asked, सर VT अलग अलग कर सकते हैं डिवाइसेस का? मैंने कहा हाँ कर सकते हैं. VT also. Keep different values for every variable over there. Whichever you want to change, play with it. And then arrive at what is the value of Vx. What this will do is, this will give you all the levers that you can play with. You could play with VBL to reduce Vx. You know that? If you want to reduce Vx, if the VBL is lower than VDD, then the potential divider is between VBL and 0 instead of VDD and 0. So Vx will reduce automatically. Noise margin will improve. Are you with me? So we just do this. We put all the possible variables in there. चाहे वो word line का voltage है, चाहे वो bit line का voltage है, just play. Just do this analysis, create an equation. Put that equation into MATLAB. Put some numbers in there and see what is happening. Word line rise करने पे क्या होता है, word line lower करने पे क्या होता है, VBL को raise करने पे क्या होता है, VBL को lower करने पे क्या होता है. Just play and experiment. The more involved analysis you do, the better your understanding will be. If you do not want to do an involved analysis, there is already an analysis given in Veste. You can just read that. But if you want to develop a deeper understanding of how a memory cell SNM or how a memory cell stability can be enhanced, do a more involved analysis. You may want to initially just put two things, VBL and VWL. VT still remains same. करके देखो. Then you say, अच्छा अगर VT भी change करते तो वो क्या होता? Just add, एक करके add करके देखो. And again, it entirely is your volition. I'm not going to evaluate this homework. This homework is already available in the classroom also. Google, जो YouTube videos हैं उसमें भी available है. I'm not going to evaluate you on this. It is for you to develop an understanding. Now, my expectation from the team that is working on the Islam compiler is that you do it. At least you do it well. Others, it's your choice. But If you really want to develop an understanding about how the SRAM cell stability can be managed, you also have to very soon start on your assignments of reading some papers on SRAMs or memories, and that is an assignment that you will have to do. Uh, so, if you understand the cell well, those papers will be a cakewalk. Otherwise, when in those papers they will say, okay, raise the word line, and therefore this right margin will improve. Now you will not know why and how. So my recommendation is do this analysis well. That is why I'm spending some time on it. But it's not going to be evaluated. Why I am not evaluating it? Because पिछली बार जब मैंने आपके assignments को evaluate करा, आपको लगा कि उनका score ज़्यादा होना चाहिए था. I'm already telling you नहीं है ये. Were the DVD assignments for you for of any value to me? No, they were only to help you, to guide you, to nudge you so that you could do your projects better. So I do not want to give a carrot to do the assignment. आपको नहीं करना मत करो. But if you're interested, please do. I assure you, it will help you in analyzing your papers, in reading your papers. It will also help you when you are doing your project later. But it's not a mandatory assignment. It's optional. Is that okay? And similarly, I want you to do this assignment for the right also. Now, the right is a little tricky thing. In right, in whichever text you see, they will only talk about the pull-up ratio. Pull-up ratio is strength of pull-up with respect to the strength of pass gate. What I want you to do is, I want you, so अब आप क्या चाहते हो इसमें? आप चाहते हो that you should get a 0 here. You want 0 to come here. And you know that pull-up was initially driven to 0. So 0 नहीं, चलो यहाँ पे आप Vy मान लो. You want this Vy to be as less as possible. At the pull-up, you know there was a 0 written. At the gate of the pull-up, there was a 0 written. Do this analysis like this and find out what is the PU ratio that you need. Okay. Then do one more thing. Instead of this 0 over here, put this Vx. Because in reality, when the write is happening, the other side is reading. So in reality, there is this going to be Vx over here. So if you've not done this, you can't do this. Then put a Vx over here and see how the magic unfolds. What happens immediately? If instead of 0, you put Vx there, something good happens. Really good happens. I want you to find that out for yourself. Is that okay? ठीक है? We have until Tuesday, coming Tuesday. 3 दिन का weekend है आपके पास. Play करो. We'll discuss this again on Tuesday. Is that okay? So now let's go to the bit cell layout. I'm already directly taking you to the modern method of laying out the memory cell. Okay. I have not seen a textbook which talks about this layout.
So in the last, okay, I said one question. So in the videos, we discuss something like VT being 3 sigma fast. Like that. What does that mean actually? What is sigma fast?
So Madhav's question is that in the videos, there was this, when you were analyzing the bump and everything, the thing that you're going to do on Tuesday next, there is this talk about VT of the pass gate being 3 sigma fast. and VT of the pull down being 3 sigma slow. What is this sigma? What are you playing this with? मतलब ये sigma क्या है?
Standard deviation.
सिग्मा स्टैंडर्ड डेविएशन किस चीज का? सिग्मा स्टैंडर्ड डेविएशन ठीक है, मैथ से हमने जोड़ लिया, किस चीज का सिग्मा है ये? एसएनएम। मैं एसएनएम का सिग्मा डिवाइस पे क्यों लगाऊंगा? This is the nominal VT that I'd want to have for my pass gate. Nominal VT for my pass gate, but any process, any manufacturing process will have some variations. And any natural process or any manufacturing process, those variations, अगर आप raw parameters की terms में बात करो, will be Gaussian. When you have a large sample set, they will be Gaussian, at least in the center region. At the edges, corners, you may see something different, but the central limit theorem tells that अगर आपका बहुत बड़ा sample set है, तो at least in the center, up till a few sigma, the distribution will remain Gaussian. Beyond few sigma, something else can happen. अभी हम उधर नहीं जा रहे. But until a few sigma, the distribution is Gaussian. So what does that mean? That means that there will be cells in which the VT of the pass gate will be fast because of Gaussian. Fast VT means this VT will be slow, मतलब lower. NMOS है. Lower VT means fast device. आप पास गेट को रेजिस्टिव चाह रहे थे, but due to variations, it is a little faster, a little stronger. Now, in the same memory cell, it can also happen that the pull down VT is a little larger. It can happen. It is probabilistically possible because they are independent devices. What does VT depend on? Dopants, oxide thickness. So some parameters might be related, but many other parameters are not related. We'll go into much more detail in mismatch and how this occurs and everything in a later class. But at least this much we've already discussed in DVD. That आप तो मोंटे कार्लो चला चुके हो पावर पे, हम क्या बात ना है, किसको बता रहा हूँ यार. So we know that there are going to be variations, huh? And there is a possibility that VT of PG could be here and VT of PD could be on that side. Even if I had targeted both of them to be at the same VT. So that is what we are saying. That assume that VT-PG is 3 sigma on the faster side, VT-PD is 3 sigma on the slower side. Let's see what is the impact on SNM, on VX, or यहाँ पे, writability, whatever. So that is why in that text also I wrote that VT को अलग-अलग मानो. Because अगर अलग-अलग मानोगे तभी वाला चीज अपने MATLAB में डाल पाओगे. If you assume it to be the same, then both have the same variable name. How will you give two different VTs to PG and PD in your analysis? So if you really want to see all the effects, make it as generic as possible. Okay. Now, as you make it more generic, it is going to be more complex also. I'm telling you, the analysis is not ऐसे हो जाएगा. But just finally, what I will tell you, finally, you will need to solve just that quadratic equation. B square minus 4AC, उसी को निकालना है और उसको आपने पॉजिटिव प्रूव करना है. That is what you will need to do. Is that okay? So, करो, खेलो थोड़ा सा, मजा आएगा. नहीं आ रहा होगा तो मत करना, आ रहा होगा तो खेलते जाना. Is that okay? Any more questions about the assignment? Or so it's not a graded assignment, it's an optional assignment. You do it, have fun. Okay, coming back to this place. So this I'm taking you directly to the modern layout. You're young people, why do you want to go into old age things? So in advanced technologies, we do not like bends. In advanced technologies, we want to keep as straight lines as possible because we're already pressed by the fact that our device feature size is very, very small, much smaller than the wavelength of light that we are working with. So in all modern technologies, this is the kind of layout topology that we use. So now we have understood which kind of devices are bigger and smaller. So over here in this particular topology, can you tell me which devices are PG, pass gates? Upper left, this one, and bottom right. These two are pass gates. Hmm? Pull downs, this one, the bigger ones, they are the largest transistors, and pull ups, the PMOS is in the center. दो ही तो PMOS है. So they're very easy to identify. So this is simply a cartoon. I've already kind of exaggerated the difference in sizes to help you identify them. What is important to note over here is that unlike a standard cell where we said that we will leave half DRC everywhere, here I have almost always, look at this over here. I've almost always pulled my features across the boundary of the memory cell. Are you able to see this? This is extremely important because we want to do sharing. We've talked about it in an earlier lecture also that in SRAM cells or in SRAM leaf cells, not just the SRAM 60 cell, but SRAM leaf cells also, चाहे वो IO का बनाओगे, row decoder का बनाओगे, whichever leaf cell you will make, you would want to do as much sharing across the boundary as possible because it is area is diamond. Okay? So even though for standard cells the area is gold and you leave half DRC only, not full DRC at the ER boundary, you can't even afford that when it comes to diamonds. So you want to do sharing. Hmm? Now, this is the first set of contacts that I'm sharing. These are the contacts for which signal? VDD. Hmm? Second set of contacts. Which signals would these be? Bit lines. They are connected to the pass gates. This one, ground. So VDD, bit line, ground, all three shared. This one, word line also shared. Do you realize all the inputs and outputs of the memory cell have shared across now? This is an internal contact. Why? Because I need to connect this node Vx to the pull up on the other side. Also the pull down on this side. And these are two special contacts. See, all of you have made layouts. Have you noticed that contacts that you draw are always rectangular? Square. But now I have made a rectangular contact. And you will notice that it is only inside a memory cell that the technology team will allow you a rectangular contact. The reason behind this is that if I were to make two contacts over here, one for the inner node of the PMOS and one for the gate of the PMOS, if I was to make these two as separate contacts and then connect them by metal, uh, I will need to keep contact to contact spacing. That will make my cell taller. Now, why is there a contact to contact DRC? Why does a technology team give you a minimum spacing between two contacts? To avoid shorting of those two contacts. Now, in this case, I know that I want to short them. I'm going to put a metal one up there anyways and short them. So do I really need to follow that DRC now? I want to short them. Do I need to follow that DRC? No. So अगर मेरे को DRC follow नहीं करना, तो I can bring them closer. Now what happens? The spacing between the two contacts becomes something like zero point 0.1 micro, something very, very small, because I want to bring them as close as possible. I want to bring them this close. Okay. And the spacing between two squares is now much lesser than the resolution of my lithography machine. It can't handle it. So I say, "Hut, let's make a long contact." So that feature isn't there at all. Because as soon as you leave that little line over there, then the lithography machine will go bonkers. So say, forget it. I will make a long contact. So long contacts are allowed because these two nodes were anyways wanted to be shorted. And for memories, area is diamond. Now, so why can't such a long contact then be allowed in when you're putting multiple contacts on a big device? No, no, no. और don't, उंगली दे रहे हैं, पांवचा मत पकड़ो. We're giving you this concession because for you area is diamond. Making a long contact still requires optimization in the technology. A lot of OPC is required to be able to make this. Okay. So we are doing this because for you area is really, really that critical, but we can't do it for everyone. Another thing, another reason why we are able to do it for you is you can tell us exactly the relative placements of all such long contacts. You can tell me about the neighborhood of such contacts. If I'm aware about that neighborhood, I can optimize my process accordingly. Now, if I allow long contacts to be used anywhere, then the cost of process optimization will be humongous. Area is anyways not critical. What you are telling me is that you want to put one lesser contact. Arey yaar, chhod na, put two contacts. Just for CAD reasons, I don't want to waste my time, energy, resources on optimizing the process. I'm optimizing it here only because area is diamond. And because there is a structure in which you will use these long contacts, I can do something about it. I will not allow it anywhere in an unstructured manner. So long contacts are allowed only inside the memory cell and nowhere else. Is this clear? So while you know that this exists, when you become if you go and design some other cells, any other standard cell or anything, you cannot use long contacts. Now, in very advanced technologies, the same material, the material of contact is tungsten. The same material is also used to make local interconnects, LIL, local interconnect layer. Okay. And that has some semblance of long contact. It's it's a contact which you can stretch. Contact you can stretch means tungsten hai, and you can make wires out of it. So in advanced technologies, people have allowed use of LIL, local interconnect, to gain density. However, there are very stringent rules around it because we're talking about the ductility and maneuverability with tungsten over there. But it is now more widely allowed in very advanced technologies only. So you might land on this side where you have such provisions, or you might land on the other side where such provisions are not there. Until you are sure that a LIL, that is local interconnect layer, exists, you cannot assume the contact to be stretchable. Even in those technologies जहाँ पे contact को या tungsten को local interconnect की तरह use करने की बात करी जाती है, even there, the DRC for the contact is square only. Are you with me? So if you need to use a rectangular contact, you make a LIL. You do not use contact layer. Even though in the backend material is going to be the same. Is that okay? So we made a long contact over here. And now we start to place metal ones. Metal ones for connecting various signals as they will come. And here again, do you notice that I'm not really covering all the contacts fully. Again, this is allowed only inside the memory cell, only because the structure is very standard, is not being changed, and only because I want to reduce area. Area is diamond. So since I am doing all such violations until metal 1 layer, whichever company you go to, they will not allow you to touch anything up till metal 1 inside your memory cells. So we'll talk about what we call as replica paths, dummy cells, and so on. So in dummy cells or in replica paths, you cannot touch anything below metal 1. All the changes that you may want to do are to be above metal 1. Now, only for poly, we may make some exceptions, but that will be on a case-to-case basis. If you want to do it, you have to come and check with me. You have to come and check with me, but in your company, you will have to go and check with the process teams over there. Is that okay? So then we come to VR1. No violations in VR1. Uh, Metal 2s, there is a VDD, there are 2-bit lines, there are stubs for the word lines, and there are stubs for ground. What this means is I will need VR2s to take my word lines in metal 3 and to connect my ground in metal 3. And I first make the word line and then I make the ground rails. Are you with me? Any questions until here? So, yes. Okay, so this question is more about sizing, that part of it. His question is that in the lectures, there was a reference that in 65 nanometer technology, the gate length that you should keep is 80 to 90. Why do you think we need to do that?
This question is 6 for 65 nanometer.
So in any technology, 65 में आप उसको 80 या 90 रखोगे, 45 में आप उसको 55 या 60 रखोगे, 32 में आप उसको 40 के आसपास रखोगे. Why do you do that? First, to reduce leakage. Because most of the cells are off at all times. So in the same area, if you can reduce leakage a little, good. Your devices are also very small. You're also violating so many things. The short channel effects are also very pronounced. So you want to reduce all those aspects. And then we will look at mismatch in one of the later classes. And then we will talk about the fact that mismatch, that is this variation of VT that we just talked about a little while back, is dependent on the area. In fact, inversely proportional to the area under the gate. Actually, inversely proportional to square root of area under the gate. Square root of WL. If I want to reduce mismatch, I have to increase WL. Width I can't increase because that increases area of the memory cell. Area of the memory cell is diamond. So length I increase. And when I increase the length, I'm also making violations in poly to contact spacing. So I increase the length, but I still say, let me use the same poly to poly spacing, center poly center to poly center spacing as I would for the minimum length devices. So what happens is, यार ये पेन दूर से नजर ही नहीं आ रहा होगा आपको. So what happens is there is this one poly, there is this other poly, and you wanted to have this contact in between. Let's say this is that pass gate pull down wala intersection. Now you said I want to increase the length of my poly. Little. So I increase the length. But I do not increase the spacing between poly to poly. Poly center to poly center. So what I'm doing, I'm actually violating the poly to contact DRC. Again, this is allowed only inside the memory cells. Don't even imagine to do it outside. Exactly the same reasons that such violations are very structured. Area is diamond, blah, blah, blah. Nothing else changes. There are many more violations that we do inside a memory cell. We shrink the NVEL width, we reduce the NVEL to active spacing. We do many, many things. Okay. But the answer to your question is that we need to do this so that we are able to reduce leakage, reduce mismatch, and also uh, not increase area. So that we do the DRC violations. तो वही मैं कह रहा हूँ ना, हम DRC वॉलेट करेंगे, पॉली टू कॉन्टैक्ट का एक स्पेसिंग दिया जाता है, हम उसको वॉलेट कर देंगे ताकि एरिया ना बढ़ाना पड़े. बट दिस अगेन यू कैन डू ओनली इनसाइड द मेमोरी सेल, प्लीज, कहीं और नहीं. इज दैट ओके? इज द लेआउट पार्ट क्लियर अंटिल हियर? एनी क्वेश्चंस ऑन द लेआउट? ठीक है. So now, do you notice that I wanted to make my word line at lower RC? So I made it wider than the minimum width. Again, it's a cartoon. I made it much, much wider than the ground rail. But I made it wider. And as I have made it wider, this ground rail and this word line have become very close. So word line capacitance increases. मैंने R तो reduce करा, but capacitance बढ़ गया. तो overall RC में I may not see as much gain as I would want to. So what we do is we say, okay, we'll clip the ground. The ground rail will not be continuous. Oh, see, now the ground rail is not continuous. So where will you get the ground supply from? From metal 4. So metal 4 has to run vertically and connect all these ground stubs. So there will be VR3 and metal 4. Metal 4 anyway होना है. You have to provide VDD also. VDD vertical जा रहा है, but कहीं से तो आएगा ना. Top level से supply तो लेना ही पड़ेगा. So metal 4 will carry the ground and it will directly give the ground to the memory cell. Is this clear? So now we say, okay, अब हमने इतना सारा sharing कर दिया. How does my layout look? So this is a layout of 2x2 memory cell matrix. In your projects, you will be expected to build a 8x8 memory cell matrix. Is this clear? Now, time and again, I have noticed that even though I have very clearly said this is the topology I want you to use, यही 6 transistors हैं, इनको इसी topology में बनाना है. No other topology. Still, there are people who want to be creative for the memory cell layout. I am telling you, this is the densest that you can go. Any other topology, if you make, either you prove to me it is denser than this, or you're getting a significant cut in the marks. And if you do prove something denser than this, then balle balle, सीधा A plus. Are you with me? Is this part clear? सीधा A plus. So do try A plus. But अगर dense नहीं है, then you have to come back to this and make this and demonstrate this. Is this clear? So I want you to try. I'm encouraging you. I'm telling you, कुछ भी और marks हो, आप कुछ भी और ना करो. You show me a denser layout topology there, A plus. We'll patent it also. Is that okay? Otherwise, come back to this topology. Yes? Yeah. So there are these. Okay, so in this layout, there are multiple structures which are shared across 4 cells. So this ground, this via, for example, this via for the ground is clearly shared across the 2 up and down cells. And when you will flip this, this will be shared on cells on this side also. So you will find many structures which are shared across two cells, like the word line contact or the VDD contact or the bit line contact. They are shared across two cells. And there are many structures which are shared across four cells. You really want to do as much sharing as possible because you want to reduce area. Is that okay? M4 will be running vertical. So the M4 will run vertical over here. It will carry ground. Another M4 will run vertical over here. It will carry ground. So every bit cell boundary, there's a metal 4 running vertically, and it will carry ground, and we'll drop that ground on every such intersection with metal 3 over there. Is that okay? So you will be making the 8 cross 8 array. So all these things will become clear to you as you will do that. Okay? So now, while I directly took you here to the most commonly used layout topology of the day, this is one topology that was used very commonly earlier. Now, this is a U-shaped active. Look at this. And just look at the number of bends and things happening between all the various metals, all of that. So this is the layout that you will see in Veste, I think. So it is no longer used anywhere. It is also dense. But because of so many bends, so many variations, it is not used anywhere. Poly में देखो एक यहाँ से bend आया इधर लेके गए, then यहाँ का एक और poly अलग है. So lots of things are there. And the structure, this is a 4x4 structure, and then this is a much bigger array. The structure would look like this. So you will see people talking about, so we'll read some papers also, because see, most of the colleges, people use only Veste and other books. They have no clue about what is happening in the real world. So you will see such papers also. Don't get worried कि अरे हमने तो ये करा नहीं. मैं आपको नहीं करा रहा, because it is no use today. Okay? So आपने नहीं करा तो अच्छा नहीं करा, क्यों फालतू में पुरानी चीज के ऊपर वेस्ट करना अपना टाइम. Is that okay? You want to do it? Anyone wants to do it? Please. Veste is there, do it. But I am not going to waste my time on this. Okay? So now, let's go to still more modern world. अभी तक हमने बात करा कि there has to be a cell ratio that you would want to maintain between the strength of pull down and pass gate. You would want to keep it at about, आप जब निकालोगे अपने कैलकुलेशंस करोगे तो आप कहीं 1.5, 1.6, 1.7, 1.3 more than 1 पे आओगे, because you know it is required to be stronger. But when you do that by the changing in size, what happens is that there is a notch that is coming, a bend that is coming because pull down is larger than the pass gate. So there is a bend that is coming. And on silicon, that results in variations. So जो भी हम थोड़ी देर पहले बात कर रहे थे, there are these two lobes. And in those two lobes, there can be asymmetry between the lobes if there are variations. Now, those variations are introduced because of such bends, because of lithography itself. See, what will happen is that over here, this would go something like this. So what happens, कहीं पे जाके आपने width W मानी थी pull down की, that W will be W minus delta W. Now, depending on how this curve moves up or down, how this bend moves up or down, what could happen is pass gate can become a little stronger, pull down can become a little weaker than what you had designed it to be. So variations will happen. So your nominal first level SNM will be high, but due to variations, when you're talking about billions of samples, there will be devices which are going to have a bad SNM also. Okay? And these are the results that Renesas showed They demonstrated that in a high density memory cell where they just kept the same width of the pull down and the pass gate. So the cell ratio is 1. Where they did that, even though even though the medium SNM was smaller, 154 tha median, but because sigma was lower, my VDD min was actually better. My overall yield